Yeah, I was trying to recall what I said on Monday during the class. I just found out I made a mistake. IDM and the fabless. You probably already forgot about that. So if I don't mention this, you don't even know. I'm just too honest. Remember IDM and fabless? What is IDM? What IDM stands for? What is fabless? Yes, yeah, integrated device manufacturer. And what is fabless? So they don't fabricate. They don't fabricate chips. Okay, so actually they are different. If you just from the name, you can tell independent means they can do everything by themselves. So what are these? Do you have any examples for IDMs? Any IDMs you know? Like Intel. NVIDIA? NVIDIA is not. NVIDIA is fabless. Oh. NVIDIA doesn't have a foundry. What was the company that had the foundry? Did I say anything about that? I didn't. What? Oh, Intel. Oh, Intel is actually IDM. So that's the mistake I made on Monday. So it's called IDM. It's independent device manufacturer. So they can do design and fabrication, which makes sense, right? Intel can do it. Do you know another one? Samsung is another one. Good example. Anyone else you think can give an example? What about TI? Texas Instrument. Where's TI? The headquarters, don't know. Yes. Maybe in Texas. Yeah. Which part in Texas? Dallas, right? Headquarters in Dallas. And TI is probably one of the pioneers for integrated circuit design in general. And we talk about TSMC, okay? I know that the CEO's Chinese name, I forgot his English name, Dr. Zhang, and he's probably 80 something years old right now, and he graduated from a graduate school in the U.S. and attended, got a job in TI in the 70s or 80s, and after like 10 years, he went back to Taiwan and started TSMC, so and now became the best foundry in the world right now. So a lot of things started from the U.S. What a great country. A lot of analog circuits, many. So I don't know if the what's the name of the op-amp we used? 720, 7 what? 741, right? Yeah, they did make that though. Is that from TI? Yeah, and just many little integrated circuits, analog, some digital ones as well. Microcontrollers. Actually, Mason was just showing me that microcontroller he found out for the little burner alert device. And there's another very popular microcontroller called MSP430. So a lot of people use it in graduate school in China. It's less popular here because you have to read a lot of libraries by yourself instead of directly loading them from all the open source library as Arduino. You can directly just load it and use. But this one you have to write a lot of drivers by yourself. But it's still very popular, and the one Mason just found was only 70 cents. 70 cents, like this. This, right? It's a big company. What about fabless? Do you have any examples? Fabless, Qualcomm, Broadcom, NVIDIA. So it's actually taking a big portion of the market because they don't have to do manufacturing, which is pretty difficult. There's only one best one is taking like 90% of the market share for the advanced chips, just one. It's very difficult. So that's why they started separate their design team from the foundry team. Intel started the integrated circuit design business probably very early in the 1970s as one of the earliest ones. So they have both. They are IDMs, but eventually they found out if they want to do both, they cannot do well for each of them. And after maybe 20, 30 years, the new companies are not trying to do both anymore. It's just too much investment into the foundry. So they either just focus on the digital design or circuit design or IP design, just design all the IP cores. So we're talking about LDOs, low dropout regulators, voltage LDO voltage regulators. There's a voltage regulator. If you input a 5 volts, like the ones we used in microcontrollers, you input a 5 volts, it regulates into like 3.3 volts for your for the voltage rating for the microcontroller. And sometimes you use the voltage regulators. We have used the 2 different ones, the 1 amp one, right, and the 3 amp one in the lab. But also, people also design regulators on just inside the chip. Okay, so if you want to achieve low power, the standard power supply is usually 3.3 volts, but your CPU core is running on 1 volt logic. So they have an LDO here to step down the voltage to 1 volt to supply the voltage to the CPU. The CPU runs at a very high frequency, which consumes a lot of power. Digital signal charge up and down, charge up and discharge whatever the circuits in there. They have parasitic capacitance and all the things. It consume power. Charge, discharge, consume power. And when you run it fast, it consumes even more power. So you want to reduce the voltage level, so you don't have to charge it up too high, because you have to dump a lot of current into the bucket, right? The capacitor in order to. So current is energy. You dump a lot of current to charge it up to 3.3 volts, and then you have to draw power out to reduce it to whatever to 0 logic. So it takes a lot of power. That's why you want to reduce the voltage, reduce the voltage high here from 3.3 to 1. It's just the logic. You don't care about the voltage level. It's not analog, right? You just need a 1, 0. So we reduce it to 1 volt, and you run the CPU at 1 volt, but you supply the chip with 3.3 volts as a standard voltage, not just for this one, but also for other chips, to reduce the power consumption. Okay, so for example, this circuit is called LDO, all right, and this one is a standard circuit. We don't have to redesign it every time. So this is called IP. Most of the time we are treating this one as IP. We just buy IPs from the companies available, whatever company is designing IP, selling these IPs, we buy it and then we import it into our design. Do you think it's making sense to make an LDO by ourselves? Have to hire another student or another employee and pay that person $120,000 a year just designing this one? I just buy it for $4,000. I actually got a quote a few months ago for our WDC CPU. I was trying to buy an LDO, but eventually our partner just said, you just supply low voltage from the pin. We're skipping that one. So we're going to buy a IC chip, which is only like probably $2 instead of buying this IP, which is $4,000. You know what I mean? So it's just for prototyping. We just buy a chip and put it on the breadboard, and we regulate it outside of the chip instead of doing it inside. Just for now, yeah. Eventually you still want an LDO inside. So this one, so you got the idea for the IP. Okay, so this is just one example for IP. And LDO is an analog. How many of you are taking analog this semester? You too? You're not taking analog? Okay. So analog circuits, designing analog circuits is important, and for now, most of the time, it's just the PLLs and it's clock generator. It's called phase locked loops. This is one of the most analog work that available on the market. For example, designing an op-amp. I don't think anyone is still designing an op-amp right now to get a job, getting like 120K a year. No, it's just buy IPs. Or maybe the company already has a library you can directly use. So designing analog circuits, it has a smaller market and opportunities to get a job right now, but it pays really well, and it's pretty irreplaceable in the future. Not too many people are able to do it and are willing to do it. So most of the time, For analog designers, they are making PLLs in the company who are making SoCs, which is a digital chip. So the analog designers are just making analog circuits. For example, PLLs as one of the most popular one to generate a clock for digital chips. Because everything we want to deal with, most of the signal and calculation using digital instead of analog anymore. It's faster, lower noise, and you can integrate a lot of components in one smaller area. So we do digital a lot, but we sometimes still need like PLLs, LDOs. These are analog parts. If you want to find a job, it's either making PLLs, but serving, you're helping the digital circuit company instead of just a pure analog company. Pretty much doesn't exist. It's just a pure analog designer. I don't think there are many opportunities available. And or IP company. There are companies that are making IPs, like the ones I got a quote for $7. That's a company making IPs. And I had so I met with another one in China this time in the summer, and he worked with a company doing digital design, but making digital IPs, not analog IPs, digital IPs, just Verilog. They code it up in Verilog, and then synthesize it and do some backend design and lay it out, right? And then put it in the box like a library to sell the library. So the IPs can be either analog or digital. If you do learn Verilog, learn VLSI, you may be able to find a job in the company making IPs. Okay, some of the fabless companies could be making IPs, just making IPs, or they are making systems. They buy IPs and put them together and design a little bit of the logic to connect all the IPs together, right? They buy CPUs, they buy IPs, and put them together and make an SoC, right? It's not that easy. It's still a pretty challenging job, but still has a lot of work. You buy these IPs, you put them together, but still afterwards you have to do a lot of timing analysis for the backend design. You'll see how that works for the Cadence Innov's tutorials later this semester. Right. So fabless, you can expecting IPs or digital design, SoC design, and the examples can be NVIDIA, Broadcom, Qualcomm. There are just so many other ones. I don't have it here. What about Apple? They don't have a foundry. They fabricate their A10, A15, whatever from TSMC. That's why TSMC is gotten so rich. They got big contracts from Apple. Okay, is Apple the biggest company with the largest market value on this planet right now? I think it's Apple. Yeah. So the top 10 largest ones in the world, I think there are like 6 or something are from the US. They have 300 million people, but still having a high standard life. All the rich countries in the world, they like all the European countries, but their population are not that large. If you have like 300 million, but still have average salary with $50,000, it's amazing. It's because all the high-tech companies are making a huge profit. We should appreciate that. Is that Apple?
Yeah, by a lot.
Yeah.
By 400 billion.
Yeah.
Their market cap right now is $2.9 trillion.
And it's fabless. So it's okay to be fabless. It's very okay to be fabless, actually. Yeah. And TSMC is also pretty large, but it's not as big as Apple. I can actually see it real quick on my phone, but I won't spend time on that. So we have some examples for fabless right now. You can name a lot, right? So a lot of opportunities are right now in fabless. It's easy to start. You just buy a server, buy Cadence, and hire a few people in there. Can start a very small company, just do fabless business. It's just too small, but a few people to do front end design, code up the digital in Verilog, You should take embedded in spring. Are you still here in spring? You should, right? Yeah, take embedded. So you can learn about Verilog, FPGAs, and front-end design and verification team and back-end design team. About 10 people, 20 people, you can form a company and try to find some investment to the company for SoC. So that's fabless, right? IDM, we got examples for like TI, Intel, Samsung, right? And what about Foundries? Foundries. TSMC. Samsung has, but Samsung's IDM. So TSMC, Foundries, what I'm saying is pure play, right? Pure play Foundries. I'm going to ask you this kind of question in the quiz on Friday. So name like a few or 2 or 3. I don't know the number, but for example, name 3 IDMs, name 3 fabless, name 3 Foundries. Is there another one? Service. Sometimes a foundry, but it's IDM, right? So I'm saying pure play, just pure foundry. TSMC is the foundry. Global Foundry is another one. And there's many of them. Micron is the foundry. They also do design actually. No, Micron is IDM. Yeah. UMC, right? TSMC. And service, what about service? Service. We talk about Muse. You can just look at their company's website and see what the business are doing. Okay, Muse, Moses, and there are many other ones like Skywater. Skywater is a foundry actually. Skywater is a foundry. Yeah, it'll be a very simple quiz. So that's the ecosystem of the semiconductor industry. I hope you guys understand it. So whenever you guys are in the interview, you know what's going on with the industry. Okay. Now let's do our DAC. Talk about DAC. So DAC stands for digital to analog converter. So you're expecting how many? You're expecting multiple inputs and one output, or one input, multiple outputs. So what you're expecting for DAC? Just one output. Why? Wait. Yeah. Yeah, so digital to analog is to analog, which means we are getting analog, right? Do we need the multiple bits for analog? It doesn't have even bits, right? It's just a one voltage. So you need one output. And depends on the resolution, you can have no matter like 3 bits, 8 bits, 12 bits, 14 bits, doesn't matter. So I have D0, D1 until D n or dn minus 1 for n bit. If it's n bit DAC. From D0 to D what? N minus 1. So I have n bits. Right? Okay. So for n bit, it's also in the VREF as a full, each the input voltage, it's analog voltage, defines the full range of it. So for n bit DAC, it has how many inputs? How many input combinations? How many combinations for the input? How many possibilities you have? How many bits? N bits, right? How many different numbers for 1 bit? 2. So totally how many combinations for, yeah, 2 to the nth, right? Okay. Input combinations. And there's a fraction, f equals d over 2n. This is one definition here. So d is a digital input word. It's going to be a digital signal, like 1, 0, 1, whatever, right? It's a digital word. And n is a total number of combinations. And V out equals f times vref. Vref just the full range. For example, we got 5 volts here. Then 5 volts times which equals, let's just write it down here. So this is d over 2n times 5 volts. Why does this make sense? I mean, let's try to understand it instead of just memorizing, the equation here, because it's very, very easy to understand. See, here's a fraction here, or you can think about this way: 5 volts over 2 to the nth times d. That's the V out. So you have 5 volts for the full range, and divided by 2 to the nth, that number of combinations. So which is like the 1 LSB 1 piece of the all the combinations, and times how many you have for the input. Which one makes more sense? Probably this one makes more sense. This is a portion of the input in the full range, right? So this is usually, if you have 3-bit, then you have 8 here, right? If your digital input is 101 in binary and times 5 volts, that becomes V out. So this is the overall range of the analog voltage it is able to offer. Okay. And this is the portion of the input in the whole range here. You have, for the input 3-bit DAC, the input digits can be from 000 to 111. Okay. That's all the possibilities over here on the top. Example, for example, a 3-bit DAC, similar to this one, a 3-bit DAC, and the input digit is 100, and vref is 5 volts. What is V out? What is F first? Right, which is 100 binary over 2 to the nth, right? Which is what? Mm-hmm. Just the half. Mm-hmm. Mm-hmm. you don't have to worry about why it works that way, because we designed the circuit to do it. So that's not a problem to worry about right now. Okay, you just need to know it does the job. You know, if you put a digital number here, then the output becomes f times zref. That's it. I'm gonna show you the R2R DAC pretty soon, so you guys know why it works that way. Because of superposition. Just came back to the original idea here. Okay, why it works that way? Because of superposition. Okay, and let's see another example. So one question here. Okay, what's the maximum output voltage you can have for this DAC? What is the maximum? How to find the maximum? Yeah, because here's your VL. That's the equation for VL, right? And the largest F will be 111 over 8. Right, so the largest VL becomes times 5, right? Will be 1 LSB less than 5. So what's the voltage for 1 LSB in this DAC? What is LSB? List significant bit, right? Yeah. Or 5 volts times this volts.
And that's like the resolution.
Yes. Yeah. The resolution as the output or input for this voltage.
Okay. Well,
output.
Yeah.
So it's going to be the smallest what you can get at the output. Yes, smallest change. Could be smallest increment or decrement. Okay, either way. Is there a decrement, that word? No? I just made it up. Okay. Yeah, makes sense. So this will be the smallest increment or change. Increment or change at the output. Right. Example here. Find the resolution for a DAC if the output voltage is desired, so this is important, is desired to change because someone is designing this circuit, So we desire a change in 1 millivolt increments while using a reference voltage of 5 volts. Think about this for a second before we move forward. I don't want to directly just dive into the solution of it. So we are designing backwards. Now the customer just gave us a specification saying you got to design a DAC and with a resolution of 1 millivolts increments. At the worst, it can be better, okay? But 1 millivolts is largest increments we can have. Yeah, if you don't consider the power consumption and all the other things, the cost, definitely the better resolution, the better performance. Right? But since they only 1 millivolt increments, so we don't have to make it like 0.1 millivolts increments. It's just overkill. So in that case, so when I'm talking about, so when people talk about this, another thing you need to know, okay? For example, in the interview, you were talking about like, I have used the ADC on the Arduino, the analog input, right? You have used that for temperature sensor in microcontrollers, and you have used probably the joystick. You'll do it in robotics too, the joystick that send the signal to the analog input to the microcontroller to Arduino as well. So there's an ADC inside the Arduino chip. Okay, so you have been using the ADC for a while, but you just don't know it. Right? There's an ADC in there. It's not a DSC, it's ADC. Similar question. If they are, so the interviewer will say, hey, it's interesting. So what's the resolution of the ADC you have used? So what's the answer? The answer should be 1 millivolts increments or very high resolution. Or I don't know. What's the answer for the resolution as a question? So what's the resolution of it? Number of bits. So if they ask you, that sounds interesting. So what's the resolution of the ADC you have used for the Arduino board? No. The ADC. You can the pins are not ADC is backwards. You just need one input and then it has multiple just outputs. But the outputs are inside the chip. The traces are being laid out in the integrated circuits. 10. Hey, yeah, 10. So Arduino's memory is 8-bit. It's an 8-bit computer, but the ADC is 10-bit. 8 is too poor. 8-bit ADC, you only use it. I don't think there's any.
It doesn't have to be.
Hmm?
It doesn't have to be like a power of 2.
Power of 2, no. Because 10-bit is not power of 2.
Yeah.
Okay. So I think the popular ones, you probably still can find 8-bit ADCs or DACs, but I think the popular ones can be, some of them can be made in like 14 bits. It's a huge difference, even though the numbers looks not a huge difference, but 2 to the 8s and 2 to the 14s is changing exponentially. Okay, so find the resolution you are expecting an answer like how many bits.
So for that one, 12.2 is
Which one? This one? How do you get the number? Yeah, let's start working on it, okay? So how do you list the equation to calculate it? You have one, let's just list the ratios. For example, 1 millivolts is a 1 LSB for the voltage, okay? And you have a full range of 5 volts also in voltage. Okay, so this ratio equals what? It's the 1 LSB, right? In 2 to the n. That makes sense? Okay, so this is the equation, so you can calculate n here. So this becomes log 2. So n equals log 2 5 volts over 1 millivolts. Is that correct? Mm-hmm. Yeah. How did you calculate that quickly? You did it. Oh, that's right. So 12 is 480 something, right?
Yeah.
Yeah. So this one equals 12.29 bits. So should we use 12 or 13? 13. With at least 1 millivolts increments or sensitivity. Not a sensitivity, this is a DA, not an AD. So 1 millivolts increments. So the resolution, find the resolution for this circuit, the resolution becomes 13, right?
You always round up, right?
Definitely, yeah. So always integers. It has to be larger than 12.
You can't do 12.
No. Yeah. Does that make sense? Any questions on this? Yeah. Input and output? No, but just in general, when you are, for example, you are trying to buy ADC or DAC online in Google, right? So the term you are going to search is 10-bit ADC, right? So you can find a lot of options in there, or 10-bit DAC. That's the resolution in general. Sometimes we also talk about the sensitivity of the ADC, which is the smallest the voltage it is able to sense, right? So the smallest the change it is able to respond to or sense. The ADC is converting analog voltage to digital, right? If you have a high resolution, you are able to figure out smaller changes. If you have a poor resolution, the analog voltage has been changing a lot, you just couldn't tell, cannot flip the digital signal. It's not be able to tell. That's a bad resolution. Okay, find another example here. It's easier, right? Just to summarize. Let's do it, even though it's easy. Find the number of input combinations and the values for 1 LSB and a full scale voltage generated for a 3-bit, 8-bit, and 16-bit DAC, and VREF is 5 volts. It's one more practice on the calculations, okay? Got to be familiar with calculations here. So now I have the first column as a resolution. Let's just draw a table here. Resolution input combinations. One LSB and the V full scale. So we just do 3, 8, and 16. Okay. How many input combinations? Let's finish the 3-bit first. Input combinations. The 8, right? 2 to the third power. What is 1 LSB in terms of voltage? Yeah. Yeah. This is VFS, full scale. How to calculate the full scale voltage? So the maximum voltage it is able to generate. Remember I just talked about just 1 LSB less than the VREF. So it becomes 5 minus this guy, right? So it's 4.375 volts. For 8-bit, yeah, it's also the number you should know actually in the interview. Sometimes if you have been working in this field for a long time, you should know that. What is 2 to the 8th? Yeah, 256. 256. And 1 LSB, and how do we calculate it? Just 5 over 256, right? Which is 19.5 millivolts. And the full scale voltage, you can calculate it either using 5 volts minus 19.5 millivolts, right? Or you can use 2 to the nth minus 1 over 2 to the nth and times 5. Make sense? This 2 to the nth minus 1 power is the maximum input that is possible for this DAC, and times 5 volts. For 16, so the number is a little larger, and I'll just write down the numbers. You don't have to, remember it or something. It's just showing you what that looks like. It's already in the microvolts range, 76.29 microvolts. It's 4.999 volts. Okay. Do I have like 10 more minutes? So now let's look at the DACs, DNLs and INLs. So before we do that, I think we should look at the, this is DAC's input and output. Yeah, I printed out from the textbook. It's from the textbook, page 942. DNL stands for differential nonlinearity. It's one of the parameters we look at for DAC to evaluate the quality of the DAC. Okay, because it's nonlinearity, so it's better to have none of them, or we expect smaller numbers of them. But unfortunately, in reality, every DAC has a DNLs. So DNL, differential nonlinearity, or DNL for short. Okay, now let's look at the input and output to find out the DNLs. What is DNL? Make sure you are still awake. What is DNL? Yeah. Okay. All right. Let's look at this one. So DNLs, even though this looks complicated, but it's very simple to calculate, right? So you look at the x-axis. These are what for the DAC? Inputs, right? Inputs, and these are outputs. Okay. It's VL over VREF. That's why they are fractional numbers. Okay. So 0, if you look at 0, it's DNL 0. It's right at the ideal value. You got 0, you got a 0. There's no nonlinearity, no difference, no error. For one input, you input a 1 here, you got a 1. So dashed line is the ideal curve. And the dots are the values you got from the DAC. Right? And you input a 2, you got a 2. Right? Input a 3, you got a 3. Did you get a 3? You input a 3, you got something on the top of the dashed line. So you are not getting a 3 as an output. And here you got an error, which or it's not called error, it's just called nonlinearity, right? You input a 3, you are not getting a 3. So now you have nonlinearities. Yeah, none of the circuits are ideal. So you have errors in there. So it's not doing the things that you expected. I think this is just random. Depends on your design. I think if you have a better design, you have smaller nonlinearities. You have a bad design, you have bigger ones. Yeah. So you put a 3, you got something else, right? And it couldn't measure it, but it's telling you that here is 1.5. So for the height here, see the step from here to here. When you change one LSB in the input, you got a bigger step. All right. For here, you increase your input by 1 bit, you are getting 1 LSB change in terms of voltage LSBs, right? You got 1 LSB as a step. So LSBs are the step size for each increment here from the output. So you should have 1 LSB for each step, or 1 LSB increment for each step. However, you got one LSB here, 1 LSB here, but you got 1.5 LSB here, right? So you have so when you are looking at the DNL, it becomes DNL3. DNL3 is 1.5 LSB minus the ideal step size, which is 1 LSB. So my question is, what is DNL3? What? Yes. So if I'm asking, what is DNL3? You look at here, you locate 3 first, and then look at it. Oh, I got a step size which is 1.5 LSB, and I use 1.5 LSB minus the standard step size which is 1 LSB to get 0.5 LSB, which becomes DNL3. Make sense? So what about DNL4? Yeah, because you can only have 0.5 LSB here. So 0.5 LSB minus 1 LSB, you are getting negative 0.5 LSB as DNL4. What about DNL5? Negative 0.75. So what about DNL6? Positive 0.75. So what about DNL7? One zero. Zero. There's no error. You got a 1 LSB here, no error. So you are looking at the step size. You are comparing the actual step size to the ideal step size and do a subtraction to find out the DNL at that location. Okay. So this is how you calculate DNLs. And there's another one, another parameter called integral nonlinearity. Integral nonlinearity, or INL for short. So the way you calculate it is you are not subtracting the actual step size. No, the standard step size from subtract the standard step size from the actual step size. So instead of doing that, you are doing the actual value. You're using the actual value minus the ideal value. You are comparing the. You are trying to find out the difference between the two heights. If I draw on the paper, it's easier to understand, right? So for DNL, I'll just draw it intuitively, okay? For DNL, you are comparing a step size. Here's the standard step size. You are doing a subtraction here, like this, right? Just comparing the step size, okay? But for INL, you compare the, so here's the baseline, the x-axis, right? Here's the 0. You got another point here. So you are comparing the absolute value instead of the step size.
So DNL is relative to the previous point?
No, DNL is relative to 1SB, and INL is relative to the previous, the actual point, not previous point, actual point. But you are right, DNL is relative to the previous point, but you don't look at the previous point. You just look at the step size, but you compare to the previous point. That's true.
So INL is how far away from the line.
That's right. Yeah, and you do the subtraction. So here's INL. It's just like integral. If you are getting errors here, you are getting more errors later, right? So now let's see. You just, because the dashed line is the ideal curve, right? And the dots, so don't look at this black dot. This black dot was from the marker. Okay, it's not. It shouldn't have any dots here from at this point because it already has a dot here on the top, right? So the dashed line is the ideal curve, and the dot here on the top is the actual output you got. So I have to use this one's absolute value minus whatever on the ideal curve, right, at this location to find an INL. But you can see it's already labeled that for you. So the difference between them two is the 0.5 LSB. And this one is right on the curve, so it's 0 for INL 2. But we have 0.5 LSB for INL what? INL what is 0.5 LSB? INL 1, right? Here is 1. INL 1 is 0.5 LSB. INL 2 is 0 LSB. INL 3 is yeah, 0.5 LSB. INL 4 is 0. INL, what is this? 5 is. So use this one, subtract the ideal one. So this is lower, that's why you are getting a negative number. Sign matters, you know, not just in INL, also DNL, we got negative numbers as well, right? It can be a smaller step. So you subtract the 1 LSB, you got a negative number. Okay, I think you guys are almost ready for the homework. Give me one more second to look at the website. Let's don't do that. I don't want to spend another 1 minute. So I think you will definitely be ready to work on the homework assignment on Friday, starting from Friday. So it's due, I think, next could be next Friday. I have to look at the calendar and make sure we have a quiz on Friday for the ecosystem, some kind of ecosystem. Just name a few companies, you know, you understand what's going on. And the lab is due Monday next week by 10 p.m. Make sure you upload everything to the website. Just start working on that earlier instead of just in case you have some issues with FileZilla, right?